Hello and welcome to today's lesson on Newton's second law. Our learning objectives for today are to apply Newton's second law in calculations relating force, mass and acceleration, explain how force, mass and acceleration are related, and then higher tier learning objectives are to describe using free body diagrams examples in which two or more forces lead to a resultant force on an object, and to explain why an object moving in a circle with a constant speed has a changing velocity. We've already talked about Newton's first law and situations where forces on an object are balanced. So what can we say about the motion of an object if the resultant forces on it add up to zero? According to Newton's first law, if the resultant forces on an object are zero, it will remain at rest or it will carry on in a state of uniform motion. We're now going to look at a situation where the forces on objects are unbalanced. What will happen to the motion of an object if the resultant force on that object is not zero? If the overall resultant force on the object is not zero, then the object will change its speed, either speeding up or slowing down, or change its direction, or it will do both, speed up and change direction. If the speed or direction of the motion of an object change, then that object is said to be accelerating. The size of that acceleration depends on two things. The first is the size of the total resultant force acting on the object, and the second is the mass of the object, which relates to its inertia. This is covered by Newton's second law of motion, which states if the resultant force is not zero, the motion of the object, its speed or direction, will change. Pause the video now and copy that down into your books. Newton's second law as an equation would be force, measured in newtons, is equal to mass in kilograms times acceleration in meters per second squared, or F equals ma. Pause the video here and copy this down in your books. Here, force in newtons is equal to mass in kilograms times acceleration in meters per second squared. Therefore, newtons is equal to kilograms times meters per second squared. A newton is a kilogram meter per second squared. Now for a worked example. We have a lorry with a mass of 8,000 kilograms. What resultant force would be needed to produce an acceleration of 2 meters per second squared? The first step is to write down what we know. We know the acceleration is 2 meters per second squared and the mass is 8,000 kilograms. And then we use the equation F equals ma. Force equals mass times acceleration. So the force is equal to 8,000 kilograms times 2 meters per second squared, or 16,000 kilogram meters per second squared, which is the same as 16,000 newtons. What force would be needed to move a trolley with a mass of 15 kilograms with an acceleration of 3 meters per second squared? Pause the video now while you work out the answer in your book. The force would just be the mass of 15 kilograms times the acceleration of 3 meters per second squared. So 15 times 3 would give an answer of 45 newtons. A boat accelerates at 1.5 meters per second squared whilst pulling a water skier with a mass of 68 kilograms. What is the resultant force on the skier while the boat is accelerating? Pause the video now while you work out the answer. Again, the force is just the mass times the acceleration, so 1.5 times 68, giving an answer of 102 newtons. Another water skier with half the mass accelerates with the same acceleration. What's the resultant force on this skier? Pause the video now while you work it out. If the mass is halved and the acceleration is kept the same, then the force needs to be halved as well, so from 102 newtons to 51 newtons. Sometimes you'll need to find the resultant force acting on an object before you calculate the acceleration. For example, here we have a force of 3 newtons upwards and 6 newtons downwards, so the overall resultant force would be 3 newtons downwards. In our second example, we have to find the acceleration of a 1400 kilogram aeroplane, which is travelling along a runway. The plane accelerates from rest in a straight line as the engines produce a constant thrust of 4,000 newtons. A constant friction force of 300 newtons acts on the wheels of the plane. The first step is to find the resultant force. We have 4,000 newtons acting forwards, but we have to subtract 300 newtons due to friction, giving us a total forward force of 3,700 newtons. So we have the force now, we also have the mass of the aircraft, and we're trying to find acceleration. If we divide the 3,700 newtons of force by the mass of 1,400 kilograms, we will find the acceleration, and the acceleration is 2.64 meters per second squared. If you find rearranging equations tricky, you can always use this equation triangle. Feel free to pause the video now and copy this into your books. A water rocket of 2.5 kilograms is launched vertically upwards from the surface of the Earth. It produces a steady thrust of 75 newtons. What is the resultant force on the rocket? Remember, you have to take into account the thrust and also the weight of the rocket, which is its mass in kilograms times g, which is 10. Pause the video here while you find the answer. So the weight of the rocket is just its mass times g, so 2.5 times 10 gives us a weight of 25 newtons. Then the resultant force is the 75 newtons of thrust acting upwards minus the 25 newtons of weight acting downwards, giving us a total resultant force of 50 newtons upwards. For the next part of this question, you need to find the acceleration using the information you already have about resultant force. If you struggle with rearranging the equations, remember you can use the equation triangle. Pause the video here while you work out the answer. We can rearrange F equals ma to make a the subject of the equation, so acceleration equals force over mass. The resultant force is 50 newtons and the mass is 2.5 kilograms, so the overall acceleration should be 20 meters per second squared. Engineers at a space centre must determine the net force needed for a rocket engine to achieve an acceleration of 70 meters per second squared. Assume the rocket is in outer space with no gravitational or any other forces acting on it. If the mass of the rocket is 45,000 kilograms, what force is required to be produced by the rocket engine? Pause the video here while you calculate the answer. So the force will be equal to the mass of 45,000 kilograms times the acceleration of 70 meters per second squared, giving us an answer of 3,150,000 newtons. You can also give the answer in kilonewtons. An object moving in a circle has to be accelerating. Even if it's travelling at a constant speed, its direction is changing. Acceleration is the change in velocity, and velocity is a vector quantity. A force is needed to cause the change in direction, the acceleration. The force is always towards the centre of a circle. In the case of the car, this force is provided by the friction between the tyres and the road. A bucket of water is spun in a circle. What do you think produces the force on the bucket that makes it move in a circle? The answer is the tension in the string. And as you can see, the tension in the string is pulling the bucket towards the centre of the circle. We now have one final problem to consider. According to Newton's third law of motion, forces always come in pairs, and those pairs are always equal in magnitude and opposite in direction. So how does anything ever move? Here we have a horse and cart. The horse pulls on the cart pulls on the horse, with equal and opposite force. Try drawing a free body diagram of the horse to explain how objects are able to move. Pause the video now while you do your diagram. Here I've included both a free body diagram of the horse and of the cart, showing the force of the horse pulling on the cart and the force of the cart pulling on the horse. I've now included the friction force of the ground pushing on the horse's hooves, moving it forward, and as you can see, the force moving the horse forwards is larger than the pull of the cart pulling it backwards, so the overall resultant force will be forwards, causing the horse to accelerate. And for completeness, I've also included the force of friction acting on the cart, pulling it backwards, but again, the force of the horse pulling on the cart is larger than the force of friction, so the overall resultant force on the cart is forwards, allowing it to accelerate forwards as well. Well, that brings us to the end of today's lesson. I hope you found it useful, and thank you very much.